There is a machine older than the internet, older than the personal computer, drifting right now through a darkness so absolute that no human mind can truly comprehend it. It has no fuel left to spare. It has no backup systems remaining. One by one, scientists have been shutting down its eyes, its ears, its senses, not because the mission is over, but because the power keeping it alive is dying 4 watts every single year. And just before they went silent, before they closed the last window humanity had ever opened into true interstellar space, Voyager 2 sent something back, something they were not expecting. Something is happening at the edge of everything we know. Not at the edge of the atmosphere, not at the edge of the solar system as it appears on textbook diagrams with neat circular orbits and labeled planets. We are talking about the true edge, the actual physical boundary where the sun's power ends and the raw, unfiltered darkness of interstellar space begins. And the only object that humanity has ever placed in that region, the only set of human-built sensors that has ever physically touched that boundary and survived to report back, is now going quiet. Instrument by instrument, system by system. The lights are going out on Voyager 2, and what it transmitted before falling into its long, inevitable silence is something that the world's most senior space scientists are still struggling to fully interpret. Think about what that means for a moment. We built this machine in the 1970s. Engineers who are now in their 80s designed its circuits with slide rules and paper calculations. It was launched on August 20th, 1977, a year when most of humanity had never seen a personal computer, and the concept of the internet did not yet exist. And yet that machine, that product of pencil and paper engineering and human ingenuity, is today more than 12 billion miles from the surface of the Earth. 12 billion miles. The signal it sends home, traveling at the speed of light, the absolute speed limit of the universe, takes over 17 hours to reach us. And what Voyager 2 has been sending back in these final operational years is not the routine scientific noise that fills most space mission data logs. It is something more unsettling, something that physicists did not predict, something that is quietly rewriting what humanity understands about the protective boundary that keeps our entire civilization alive. But here's where it gets strange. To understand what Voyager 2 has actually warned us about, you have to understand what it crossed. In November of 2018, Voyager 2 punched through a boundary called the heliopause, a region most people have never heard of, and yet one that is arguably the most important structure in the entire solar system. The heliopause is not a wall. It is not a visible line in the darkness. It is the point where the solar wind, the constant stream of charged particles, magnetic fields, and plasma that the sun blasts outward in all directions, finally runs out of momentum and cannot push any further against the pressure of interstellar space. Everything inside the heliopause is, in a very real scientific sense, our solar system. Everything outside it belongs to the galaxy. And when Voyager 2 crossed that line, it became the second human-made object ever to do so, following its twin Voyager 1, which made the same crossing in 2012. 2 machines. 2 ambassadors from a civilization on a small blue dot. And what they found on the other side was not what anyone expected. The data that came back from the crossing was published across 5 major research papers, and it sent ripples through the astrophysics community that are still being felt today. The interstellar medium, and the space beyond the heliopause, was hotter than the models predicted, not slightly hotter, dramatically hotter. According to published findings confirmed in late 2025, both Voyager probes detected temperatures at the heliopause boundary reaching somewhere between 30,000 and 50,000 Kelvin. Unat! A blazing thermal wall at the very edge of the solar system that the theoretical models had not accounted for. Read that again. There is a wall of superheated plasma sitting at the boundary of our solar system, and our best scientific models did not predict it was there. That fact alone should make every person on this planet stop and reconsider how well we truly understand the space around us. But that is just the beginning of what Voyager 2 has been reporting. Plasma density. That is the next piece of the puzzle, and this one carries implications that extend far beyond academic interest. When Voyager 2 crossed the heliopause, its plasma science instrument, one of the most sensitive ever placed on a spacecraft, detected something unexpected on both sides of the boundary. The plasma, on the interstellar side, was not behaving the way the equations said it should. It was denser than predicted. It was compressed. And the compression was coming from outside, meaning that something in interstellar space was pushing back against our heliosphere with more force than previously modeled. Published data from Nature Astronomy confirmed that the plasma in the boundary region slowed, heated up, and reached a density twice as high as typical plasma found deeper in the heliosphere. Twice as dense. Something out there is pressing inward. Something is squeezing the bubble that protects us. And this is where everything changes. Because the heliosphere is not just an interesting scientific structure. It is the reason life on Earth exists at all. That bubble of solar wind and magnetic fields that the sun creates around our entire planetary system acts as a shield, a vast electromagnetic barrier that deflects the most dangerous cosmic rays streaming in from the rest of the galaxy. These are not the rays your doctor warns you about with a lead apron. These are galactic cosmic rays, the high-energy remnants of ancient supernova explosions, accelerated to nearly the speed of light and carrying enough energy to damage DNA, disrupt electronics, and fundamentally threaten the biological systems that evolution spent billions of years constructing. Without the heliosphere, Earth would be bathed in them continuously. With the heliosphere, most are deflected or slowed before they reach us. The heliosphere is not just the edge of the solar system, it is the reason you exist. And what Voyager 2 has been detecting in its final operational years suggests that this shield may be under pressures we are only beginning to measure. What most people are not seeing in the mainstream coverage of these findings is the timeline pressure that makes all of this uniquely urgent. In March of 2025, NASA was forced to make a decision that had been dreaded for years. Engineers at the Jet Propulsion Laboratory in Pasadena, California, shut down Voyager 2's low-energy charge and particle instrument, a sensor that had been functioning almost without interruption for 48 years. This was not a malfunction. This was a calculated, agonizing scientific triage. The plutonium-238 core that powers Voyager 2, a radioactive thermoelectric generator that converts the heat from decaying nuclear material into electricity, has been losing approximately 4 watts of power every single year since launch. By 2025, the margins had become so thin that engineers could no longer power all remaining instruments simultaneously. Something had to be shut off, or the entire spacecraft would go dark. And the cosmic ray subsystem, another crucial sensor, is scheduled to go offline in 2026, right now, this year. The window through which we have been watching the edge of the universe is closing, and it is closing fast. But here's where it gets worse. Because what Voyager 2 was measuring with those instruments before they were shut down is not a static, stable picture. According to data analyzed and published papers through late 2025 and into 2026, the very local interstellar medium, the region of space through which Voyager 2 is currently traveling, is not a calm, unchanging void. It is dynamic, it is active, it responds to forces. And one of those forces is our own sun, solar cycle 25, the current 11-year cycle of solar activity, peaked approximately around mid-2025, making it one of the stronger solar maximums in recent memory. When the sun reaches peak activity, it hurls massive eruptions of charged particles and energy outward in all directions. Those eruptions travel across the solar system, compress the heliosphere from the inside, and eventually send pressure waves propagating outward through the heliopause and into the interstellar medium. Scientists had calculated that a major solar-driven shockwave launched during the 2025 solar maximum would reach Voyager 2, which was sitting at approximately 140 astronomical units from the Sun as of July 2025, somewhere around the year 2031. Voyager 2 is literally traveling into the path of a pressure front driven by our own star, and if its instruments are not fully operational when that front arrives, we will miss one of the most important scientific measurements in the history of space exploration. According to informed sources in the heliophysics research community, the significance of this timing cannot be overstated. The last time a comparable solar maximum sent waves into the interstellar medium, Voyager 1 was the only probe positioned to measure the results. Those measurements revealed something unsettling. The interstellar medium was responding in ways the models had not predicted, with plasma density patterns and shock structures that required entirely new theoretical frameworks to explain. Now, as another wave of solar energy propagates outward, Voyager 2 is positioned on a different trajectory. Below the ecliptic plane, covering different regions of the heliosphere, and its remaining instruments are the only sensors capable of measuring what happens when that wave arrives. But those instruments are running out of time and power to receive the impact. Think about the larger implication of what is being described here. Humanity launched 2 probes into space nearly 50 years ago, and in a cosmic stroke of luck, those probes happened to reach the boundary of interstellar space at exactly the right moment in human scientific development, when we had the computing power to process their data, the theoretical frameworks to interpret their findings, and the deep space network infrastructure to maintain communication across billions of miles. The window of scientific opportunity those probes represent is not infinite. It is closing in real time. And what they have already told us in these final years of operation is not reassuring. The environment beyond the heliosphere is hotter than expected. The pressure on the boundary is greater than modeled. The interstellar medium is not a quiet, stable backdrop. It is a dynamic, variable environment that pushes back against the very shield that makes our planet habitable. What the real story is, and what the mainstream science headlines tend to bury in technical language at the end of articles that most people never Finish reading is that our understanding of how protected we are is fundamentally incomplete. For decades, the heliosphere was treated as a given, a constant, a reliable shield that had been in place for as long as the sun had existed and would remain in place for billions more years. But the data Voyager 2 has been sending back does not support a picture of perfect stability. It supports a picture of a dynamic, interactive boundary that responds to forces both from within our solar system and from the broader galactic environment. And the galactic environment, according to everything the Voyagers have taught us, is far more energetic, far hotter, and far more actively pressing against our bubble than the comfortable models of the 20th century assumed. Consider the cosmic ray problem. This is the detail that the scientists who study this for a living will tell you quietly keeps them thinking. Galactic cosmic rays, the ones the heliosphere deflects, don't arrive in a constant uniform stream. Their intensity varies based on how compressed or expanded the heliosphere is at any given moment. During solar minimum, when the sun's activity and outward pressure weaken, the heliosphere contracts slightly and more cosmic rays penetrate inward. During solar maximum, the reverse happens. But here's the layer that Voyager 2's data adds to this picture. If the interstellar medium outside the heliosphere is also varying, if there are pressure waves, plasma density fluctuations, and structural changes in the region just beyond the heliopause, then the heliosphere is being squeezed and shaped not just from the inside by the sun's activity cycle, but from the outside by forces that originate in the broader galaxy. And if those external forces intensify, even temporarily, the consequences for cosmic ray penetration into the inner solar system are not trivial. They are measurable. They are real. And we currently have almost no way to monitor them because the last sensor capable of doing so is being shut down piece by piece on a probe that was built before the first generation of personal computers existed. According to the Voyager project scientist Linda Spilker at JPL, the team's own words capture the urgency better than any external analysis can. Every minute of every day, the Voyagers are exploring a region where no spacecraft has gone before, and every day could be their last. But that day could also bring another interstellar revelation. Those are not the words of a complacent scientific mission in its twilight years. Those are the words of researchers who understand that the data still coming in from these fading machines could be among the most important measurements ever made by human instruments, and who are watching the power. Margin dropped towards zero with the full knowledge that there is no successor. There is no replacement mission already positioned to take over. The next deep interstellar probe, if and when one is built, would take decades to reach the distances the Voyagers have already covered. The data gap that will open when Voyager 2's instruments finally go dark is not a gap that will be filled in 5 years or 10 years. It will potentially remain unfilled for a generation. And this is where everything gets darker and more complicated and more important all at once. Because the world right now is not exactly investing in the kind of long-duration, multi-decade scientific missions that the Voyager program represents. The geopolitical and economic landscape of 2026 is one in which space programs around the world are competing for resources. Commercial interests are increasingly driving launch priorities, and the patient, unglamorous science of deep space monitoring competes for funding against flashier missions with more immediate media appeal. The Voyager program costs approximately $6 million per year to operate, a figure that would barely register as a rounding error in most national defense budgets. And yet, its scientific return is arguably unmatched by any other active mission in human history in terms of the fundamental questions it is answering about our place in the galaxy. The question of whether it will remain funded, whether the Deep Space Network will maintain the antennas required to hear Voyager 2's increasingly faint signal, is not a purely scientific question. It is a political one, and political questions in the current global environment do not always resolve in favor of the long view. There is another dimension to what Voyager 2 has transmitted that almost never gets discussed in the news cycle, buried as it is beneath the constant noise of geopolitical conflict and economic uncertainty. The probe carries something on its physical body that transforms it from a scientific instrument into something more: the golden record. A 12-inch gold-plated copper disc, encoded with sounds and images selected to represent the diversity of life and culture on Earth, with greetings in 55 languages, with music from Bach to Chuck Berry, with diagrams showing the location of our star and the biology of our bodies. It was placed on Voyager 2 in 1977 on the extraordinary chance that someday, somewhere, something would find it. And that machine, carrying that message, has now traveled further than any human-made object in history, drifting silently through interstellar space, carrying our species' most ambitious introduction in the darkness between the stars. Whatever Voyager 2 has sensed, measured, and transmitted back to us in these final years of operation, it has done so as not just a scientific instrument, but as a messenger. And the message it has sent home is one that demands our full attention. What the transmission from the edge of interstellar space is really telling us, if we're honest and rigorous about interpreting what the data shows, is that the environment our solar system occupies in this galaxy is more complex, more energetic, and more variable than our models assumed. The heliosphere, our shield. AOS is not a passive, static structure. It is actively being shaped by pressures from both within and without. The boundary it maintains is being tested continuously by the physics of the surrounding galactic medium. And we are just now, for the very first time in human history, developing the instruments and the data to understand how that testing works. Voyager 2 gave us that window. It gave us measurements that no theoretical model could provide. Direct, in situ sampling of the actual conditions at the actual boundary where our solar system ends and the galaxy begins. And those measurements showed temperatures hotter than expected, densities greater than modeled, plasma structures more complex than any simulation had produced. This is not a minor correction to the existing understanding. This is the kind of data that forces scientists back to the drawing board on fundamental assumptions. The implications for Earth are not immediate. Nobody is suggesting that the heliosphere is about to collapse or that cosmic rays are about to overwhelm our atmosphere next Tuesday. But the appropriate response to not an immediate danger is not complacency. The appropriate response is sustained attention, continued monitoring, and serious investment in understanding the mechanisms at play. Because the timescales on which these processes operate are not human timescales. They are geological and astronomical timescales, and the consequences of being caught unprepared for changes in those processes could extend far beyond the lifetime of any current political administration. What Voyager 2's data has done is reveal that those processes are real, that they are measurable, and that they are actively occurring right now at the edge of the structure that protects all life on this planet. And that is not a cause for panic. That is a cause for the kind of serious, long-term, species-level attention that we have historically been very poor at sustaining. As of April 2026, NASA has shut down yet another instrument, this time the low-energy charged particle experiment on Voyager 1. 7 of the original 10 instruments on each spacecraft have now been deactivated. The engineers at JPL believe that with careful power management, at least one science instrument on each Voyager could remain operational into the 2030s. The Deep Space Network, the global array of radio antennas that maintains communication with these probes, may be able to hear their signal until approximately 2036, depending on how the power margins hold. After that, silence. The machines will keep traveling. They will not stop. There is nothing to slow them down in the vacuum of interstellar space. But they will no longer be able to report back what they find. They will pass deeper into the galaxy, carrying the golden record and the accumulated weight of everything they represent, and we will receive no further dispatches from the frontier. What happens next in the world's scientific understanding of the heliosphere and the interstellar medium depends on decisions being made right now. New simulations are being developed. Ground-based and space-based telescopes are being directed at the outer heliosphere to try to detect evidence of the plasma structures and pressure patterns that Voyager 2 measured directly. Scientists are working to build theoretical frameworks that can account for the unexpected temperatures and densities the probe recorded. But all of this is modeling and inference. None of it is the same as having a physical sensor in the actual environment, measuring the actual conditions in real time. The difference between a model of interstellar space and a direct measurement of interstellar space is the difference between a map and the territory. Voyager 2 gave us the territory, and we are in the process of losing that access forever. There is a question that nobody in the mainstream conversation seems willing to ask directly, but which the data makes unavoidable. If the interstellar medium is more dynamic than we believed, if it varies, fluctuates, and responds to forces we are only beginning to understand, then what are the long-term consequences for a heliosphere that is itself not perfectly stable? What happens in a scenario where a period of reduced solar activity coincides with a period of increased external pressure from a denser region of the interstellar medium? These are not science fiction questions. These are questions that the data Voyager 2 has already transmitted makes legitimate and urgent. The heliosphere has varied in size and shape throughout Earth's geological history. Periods of reduced solar activity in the past have been associated with increased cosmic ray flux reaching the inner solar system. And some researchers studying geological records have identified correlations, still debated, still being investigated, between periods of high cosmic ray flux and significant events in Earth's climate and biological history. The picture is incomplete. The correlations are not certainties, but the fact that we are only now, for the first time, getting direct measurements of the conditions at the heliosphere's boundary means that the picture has been incomplete all along. What Voyager 2 transmitted from the edge of everything is not a simple warning in the dramatic sense of that word. It is something more subtle and in many ways more profound. It is the universe's way of telling us that we live inside a bubble we do not fully understand, at the edge of a galaxy that does not particularly care about our existence. and that the shield between us and the full force of that galaxy is a dynamic, variable structure that we are only just beginning to measure. Every data packet that still arrives from that fading probe, taking over 17 hours at the speed of light to cross the distance between interstellar space and the antennas of the Deep Space Network, is a piece of information that could not be obtained any other way by any other means. And those data packets are becoming rarer. The instruments generating them are being shut off one by one. The power keeping the systems alive is diminishing at 4 watts per year with mathematical certainty. The window is closing. And the deepest question, the one that will hang unanswered long after the last signal from Voyager 2 fades into the background noise of the cosmos, is whether we paid close enough attention while we still had the chance. Whether the data that came back from the boundary of everything was treated with the seriousness it deserved. Whether the institutions and governments and scientific agencies of this civilization made the decisions, allocated the resources, and built the successor missions that the findings demanded. Or whether the most extraordinary scientific instrument humanity ever sent into the unknown quietly ran out of power while the world was looking elsewhere, leaving us with partial answers, incomplete maps, and the unsettling knowledge that there are questions at the edge of our solar system that we may not get another chance to ask for a very, very long time. The probe is still out there, right now, moving at approximately 35,000 miles per hour through a darkness that no human eye will ever directly observe. Its signal, growing fainter with every passing year, still reaches us. And what it is saying, in the language of plasma densities and magnetic field readings and particle counts, is that the universe is stranger, more energetic, and less predictable than we assumed, that the boundary that protects us is real, but it is not invincible, that the space beyond our solar system is not a gentle, empty void, but a dynamic environment that presses back against everything we have built here, and that we have one machine, one single human-built object, positioned to measure that environment directly. One machine, running on nuclear decay, losing 4 watts per year, being shut down piece by piece, sending its transmissions across 17 hours of empty space, and still, somehow, telling us things about the universe that no other method of observation can reveal. This is not science that belongs in a footnote. This is not a story that should be crowded out by the noise of any news cycle. This is the edge of everything humanity knows, reported back by a machine that should not still be working, built by engineers who could not have imagined what it would find, carrying a record of everything we are into a darkness that has no end. Voyager 2 sent its transmission. The question is whether we were listening, and whether we are capable of acting on what it told us before the signal disappears forever.